In this video, we consider the ideas behind the Fundamental Theorem of Calculus. I'm going to start by drawing a graph, and I'll use this graph to illustrate a good deal of what comes next. I'm calling the horizontal axis the t-axis in this graph, and I want to show a function with a curve, which we're going to name y equals f of t. I'm picking a place on the t-axis, doesn't matter where it is, I'm calling it t equals a, and another place further along called t equals b. We'll be interested in the area between the function and the t-axis from the starting point of t equals a to the ending point of t equals b. As you've seen in previous videos, this area can be represented by an integral, a definite integral, where we integrate from t equals a to t equals b, integrating the function f of t dt. Now we're going to consider changing this graph around a little bit. We're going to keep the same t-axis, we're going to keep the same starting point at t equals a, and we're going to keep the same curve, y equals f of t. But that ending point, t equals b, we're going to consider what if it moves around a little bit. Like maybe I just scoot it over. Well, that would change the area. The area depends on all of those things, the t-axis and the curve and a and b. But if we keep the others constant and only change b, we get a different area for different values of b. Things you're going to change are called variables, and it's traditional in mathematics to use letters from the end of the alphabet to represent your variables. T, U, V, W, X, Y, Z. Things you're not going to change are called constants, and it's traditional in mathematics to use letters from the beginning of the alphabet for constants. A, B, C. So now, if we're going to be moving our ending point, maybe we shouldn't call it B anymore. B stands for a constant. So we change the name of that ending point to X. And the integral now doesn't go from A to B, it goes from A to X. And we find that the area is the integral from a to x of our function. The area depends on the stopping point, x. So it isn't just area, it's area as a function of x. Keeping the same t-axis, the same curve, y equals f of t, and the same starting point at t equals a, the area between the curve and the t-axis is a function of the stopping point, t equals x. So we have area as a function of x, and as soon as we have a function in calculus, we always want to know what is its derivative. I want to know the derivative of this area function. But I don't have a formula for the area function. I can't use the product rule or the chain rule or the power rule or anything like that. I don't have a formula. So I'm going to go back to the basic definition of the derivative. The derivative with respect to x of the function a of x is the limit as h approaches 0 of a at x plus h minus a at x, the whole thing divided by h. Now what is that? I don't have a formula, I have a picture. So let's look at the picture. What is a of x? Well, a of x is the area with a stopping point at x. So that's the area inside this green here, the green slashes. That's the area a of x. It's the integral from t equals a to t equals x of f of t dt. And then what's a of x plus h? Well, we have to find x plus h. Starting from x, we go forward a little bit, called h, and we get to x plus h. And if that's our stopping point, we again can get an area. This time I'm doing it in red with dots. But this is the area a of x plus h, the area that you get when you stop at the point x plus h rather than the point x. So now, taking this back up to our algebra here, a of x plus h is that whole red region, which includes the green and a little bit more. And a of x is just the green region, not that little bit more on the end. And we're supposed to subtract a of x plus h minus a of x. And so when we subtract, we're left with just that little piece on the end. That is the area that's a of x plus h minus a of x. Now, it's almost a rectangle. The top, yes, is a curve, but it's pretty close to a rectangle, and the area of a rectangle is height times width. The width of this rectangle, of course, is h. And when you cancel the h, you find out you're looking just at the height, the limit as h approaches 0 of the height of that curve. Well, the height changes over that little space from x to x plus h. It's a little lower at x, it's a little higher at x plus h. But as h approaches 0, the x plus h end comes back to hit the x end, and there's really only one point left, which is x. As h approaches 0, the limit of the height is simply the function value at x. So we've discovered that the derivative of the area function equals the height function, the function that describes the curve, at x, that is the point where the area stops. This statement, that the derivative of the area function gives the function that is the curve on top of the area, is a profound and important statement, part of the fundamental theorem of calculus. It relates two important things in calculus. So let's look first at where we got this area function. We started with f of t, that's a curve, and we integrated it and got this area function a of x, that is the integral from a to x of f of t dt, the area under the f of t curve from a to x. Then we differentiated that, and we got f of x. Now, what is the derivative? It's the slope of a line tangent to a curve. So the integral takes us from the function f to the area a, and the derivative takes us from the area a back to the function f. There's a different variable in it now, but it's the same function. And that says that the process of finding the area underneath the curve and the process of finding the slope of a line tangent to the curve are in some way the same thing run in opposite directions. That's not obvious when you first look at it. What's the connection between the area under the curve and the slope of the line tangent to the curve? Not obvious, and yet they do turn out to be exactly the same thing run in opposite directions. That's a fundamental concept called the Fundamental Theorem of Calculus. In the next video, we'll consider how to take this information about the relationship between the derivative and the integral and use it to calculate some integrals to find the exact value of some areas between some curves and the horizontal axis.